Hello, everybody. Thank you very much for the invitation to the 10th World Congress in Probability and Statistics. My name is Vlad Margarint. I'm from NYU Shanghai, and today I'm going to talk about rough path theory and the stochastic Loebner equation. So I'm going to talk about two works. Actually, the first one is a joint work with Dmitry Belyaev and Terry Lyons. It's called Continuity in Kappa in SLE theory using a constructive method and rough path theory. And the second one is a joint work with Terry Lyons and James Foster, and it's called an asymptotic radius of convergence of a Loebner equation and new simulations of SLE traces via splitting. So since I'm talking at the rough path section of this Congress, I'm going to skip the details, the introductory details on the rough path part, but I'm going to focus on the introductory details on the SLE theory. So what is the Loebner equation? The Loebner equation appears in the following context. I have a non-self-intersecting curve that is this gamma up to 0t, and I cut basically the upper half plane with this curve, and what I get here is a simply connected domain that is the complement of this curve that can be mapped using a free real parameter family of maps GT back to the upper half plane. And these maps actually can be chosen to be unique when I specify the behavior of these conformal GT maps at infinity. So we can talk about unique GT maps, unique conformal GT maps that map this this simply connected domain back to the upper half plane. And looking at this green point here, they will be mapped to GT of gamma t. This is the image of this green point here. So as I let this dynamics evolve in time, I'll get a dynamics in the space of conformal maps GT that remove all the time this gamma t growing curves. And this is captured actually by the forward Loebner differential equation. So this dynamics in the left is called the forward Loebner differential equation. And this dynamics on the right, the dynamics on the HT maps, is a backward version of this. So this is with this minus here, this is the difference. It's a time reversed version of this dynamics. So as you can see, this is just with this minus difference here. As you can see, the format is similar. This GT prime of Z, this is the derivative in T, and this UT here is the continuous time function that you obtain by really removing this curve. So one can start also differently. One can start from the forward Loebner differential equation and ask if you can reconstruct this geometric image from before. In this specific talk, we're going to work with this backward Loebner differential equation, and more specifically with UT being square root of kappa Brownian motion, where this is a real valued Brownian motion, and this kappa is greater or equal than 0. We can actually rephrase this backward Loebner differential equation as this dynamics that I really define big Z of t as this shift with square root of kappa bt. So these two dynamics here and this one are equivalent. We're going to talk also about the SLE curves. So what are the SLE curves? So I'm looking here at this object gamma t that is the limit when y goes to 0 plus of gt inverse, and this is the inverse in z. So I'm really looking at the inverse in z of these maps. Evaluated at iy plus square root of kappa bt. If this limit exists and is continuous in time almost surely, then I call this object that exists almost surely in a continuous function and is a continuous function of time the SLE trace. This inside the SLE literature is proved to exist, so that this limit exists and is continuous in time. First was proved for kappa different from 8, for all kappa positive but different from 8 by Rode and Schramm, and later also for kappa equal to 8 by Lawler, Schramm, and Werner. The next question is for you to get more intuition is how does this behavior of the SLE traces depend on the parameter kappa? And it turns out that the trace can be proven to be simple almost surely for kappa up to 4, has the SLE trace, this object that exists almost surely, it has double points for kappa between 4 and 8, and for kappa greater or 8 than bigger is a space filling curve almost surely. So this is the SLE object, the SLE trace that we're going to also discuss later on. For the beginning, I'm coming back to the backward Loebner differential equation, and I would like to see this as a rough differential equation. So This is again a rephrasing of the backward Loebner differential equation, where I can also rephrase it as this dzt is vzt dxt, where v of z has these two vector fields, v0 and v1, that are minus 2 over kappa z d over dz. This is the first vector field, and the second vector field that is d over dx, is this horizontal movement corresponding to this part. Well, and xt in this new notation is the pair t and bt, where t is a bounded variation part and bt is a one-dimensional standard Brownian motion. Here, for you to get more intuition, I also draw what is happening with the thin rectangle if this dbt part is missing. So basically, this is the dynamics under only this part of the story. The dynamics is moving points upwards. And the Brownian part, as you can see, gives some stochasticity horizontally once you add it on top of this picture. The first result that I want to mention is that given the format of this vector field, so once you start away from the singularity, this backward Loebner differential equation can be seen as a rough differential equation. And in particular, you can prove that it has a unique solution that is continuous in the p variation topology for p between 2 and 3 that corresponds to this part, to the Brownian part that is the roughest part. The solution is continuous in this p variation topology in this square root of kappa parameter. So today's focus is going to be about this continuity in kappa of the solutions and of the traces, and about approximations of this curve, of these SLE traces. So for the moment, I hope I convinced you that we can show actually the continuity in kappa of these solutions. But what about the SLE traces? These are the singular objects for this. So before we were really outside of the singularity. Right now we are looking towards the singularity, because in order to define this object we have to pass through the limit. However, here we use a different machinery. It has we square root interpolate the Brownian driver in this Loebner differential equation. So we will approximate this square root kappa bt by square root interpolating on uniform time intervals, and we will show that the corresponding traces are close to the limiting SLE traces, and we will show also that these limiting SLE traces are also continuous in kappa for kappa between 0, 8, and 3 in this sense. So the subnorm, the difference between them, where kappa j is a sequence converging to kappa, is going to 0. And moreover, the curves that you obtain by this approximation for two different values of kappa, if you do square root approximations of the drivers, you will get two different curves that are also close to each other. I would like to remark actually that the same result was obtained by Fritz, Tran, and Yuan using different methods. However, we prove, I guess, that the main point here is actually that we recovered this continuity in kappa constructively. So we show also how these approximations at the level of drivers behave as you move this parameter kappa. Some short elements of the proof. After that, of course, we can discuss more the Q&A session. So for the first part, we can use actually that t comma bt has a geometric rough path lift, since this is what is called the Young pairing in the book of Fritz and Victoire, multidimensional stochastic processes rough paths. Since t is of bounded variation and Brownian, this is a one-dimensional Brownian motion. So given the format of the vector fields, we can apply the universal limit theorem. For the second part, we need to use something else. So here we are going to do square root interpolation. This is how a square root interpolation really looks for a generic ut driver that, of course, we're going to apply for ut being square root of kappa bt. But in general, this is the square root interpolation. So this is a function that really on this uniform size 1 over n time intervals approximates your ut function. And is really equal at ut k plus 1 and ut with your function. Why do we use square root interpolation? Because for these specific drivers of this form, we can solve the Loebner equation explicitly. So we have an advantage that for c square root of t plus d, for this type of drivers, one can solve the equation explicitly. The proof really follows by comparing gamma 1 and gamma 2. These are two SLE traces for parameter kappa 1 and kappa 2 by a triangle inequality. This is gamma 1 that you compare with the square root approximation of the kappa 2 curve, and this is kappa 2 curve compared with the square root Brownian motion kappa 2 approximation. So this is something that was already done in the literature, because this is something more natural to ask. And for this part, we have to prove new things. And this is actually the one of the main deterministic results that we use, that we further adapt to the Brownian motion, is that if you the difference between these maps evaluated at the two different points can be bounded by a quantity like this. This is a version of an estimate that was obtained by Wiklund, Rode, and Wong. And as you can see, this estimate depends on this YTY, that is just a function, and that of the subnorm difference between these two drivers, as well as the derivative of these maps. And in order to control the derivatives in Z of these maps, we will look at the following uniform estimate that was actually obtained, very nice estimate that was obtained by Fritz, Tran, and Yuan for kappa between 0 and 8/3. This is, long story short, one of the short stories of the proof. For more details, we can discuss in the Q&A section. I'm right now moving to the second part, that is the backward Loebner differential equation and stochastic Taylor approximations. And here I'm interested in a different story, that is the approximation of this backward Loebner differential equation in this stochastic Taylor manner. So this VI1 and VIK can be either of this V0 or V1. So here I'm having all the possible combinations, as in the typical stochastic Taylor approximation, and this is the signature of my pair path T, BT. For this part, we use actually the notion of Pyrov paths, a la Gyurko, and it's because we need actually that the T and the DBT part come with two different regularities, and this is captured here by this notion of degree. So here I'm looking essentially at how can I control these terms given the fact that every possibility can appear. And I'm interested in evaluating this difference between the true dynamics and the approximation. And for this, we have the following two ideas. First of all, we can control, given how many DT and DBT entries, so DBT is captured by the N entries, DT by the M entries, what is the size of these compositions of vector fields. And moreover, we can prove using this type of lemma and the behavior of the iterated integrals, we can prove the following estimate, that actually the difference between these two is bounded by epsilon for time between 0 and epsilon squared. So this L2 version can actually be proved also in the absolute value sense using extension theorem from rough paths. But I prefer to really present you this L2P version, because something very interesting happens here. This is why it's called an asymptotic radius, because if we go with step size a little more than epsilon squared, so up to epsilon 2 minus delta, as we can see here, the order of these terms that appear in these approximations is epsilon to the power 1 minus delta, this degree 1, 2 of the path. So this actually, for terms of higher degree greater than 1 over delta, this is of order 1 over epsilon to some positive power, while the true dynamics is just order epsilon. So they can't really be close to each other. So this is actually how much you can go in this time interval in order to really be sure that you don't have this high order term that start to really give you trying to approximate something small with something gigantic. So I hope we can discuss more in the Q&A section. Thank you very much for your attention and for the invitation to this conference, and of course for all the opportunities that I got inside this community.